Hello. Uh, okay, again today we're going to look at the Kirchhoffs laws, and this is Mr. Mugala again. Now there's some circuit elements that we need to understand before we dive into the concepts of the Kirchhoffs laws. There's what we call the node, the branch, and the loop. And apparently these terminologies, they come in very handy whenever we are dealing with the circuits and the application of laws such as Kirchhoffs laws. So now what is a node? So a node is any point where two or more circuit elements are connected together. So wires usually have negligible resistance. So each node has one voltage with respect to the ground. Okay, just take it as that. So what is a branch? A branch is a circuit element between two nodes. So if we have a circuit element between two nodes, that becomes a branch. What is a loop? So a loop is a collection of branches that form a closed path returning to the same node. So a loop is a collection of branches that form a closed path returning to the same node without going through any other nodes or branches twice. Okay. Now, for example, we have a question that says how many nodes, branches, and loops are in this case, right? Now you can see here that we when it comes to the nodes, we've actually mentioned here that a node is any point where two or more circuit elements are connected. So for example, we have between this circuit element, which is the voltage source, and between that circuit element, which is a resistance. So we could have that one right here as our node. Alright, and between these two circuit elements here, between this circuit element and that circuit element, we could have that node right there. Now it's very much important to understand that between this point and that point, we may not have a circuit element. However, there is a circuit element between this point and that point. So what does that mean? And also we could have between this element and that element, we could also have a node somewhere there. However, these nodes that exist between elements that exist where there are no elements, they're treated as one node. So if we were to ask ourselves how many nodes are here, I could say that there is this node and there's this one node here, because there's not any circuit element between the two, and this node and that node is also treated as one node. And therefore, if we have to look at this, we can say that there are three nodes. So there is one node here, and actually we can even say that from this end up to the far end, there's just one node, because if I put a node here, if I put a node here and I put a node here and I put a node there and I put a node here, these will not be treated as nodes because the node has to exist between circuit elements. So all of these will be treated as just one node, and on top here, all of that will be treated as what? As just one node. Remember, we said that a node is any point where two or more circuit elements are connected. So if the circuit elements are not connected, they're not found there, those could be treated as just maybe one node because they have got the common configuration. Now, what is a branch? So a branch is a circuit element between two nodes. So if we have a circuit element between two nodes, we have that one to be called what? A branch. So for example, this is one branch, and there was a node here and there's a node there, right? And also this is like one branch because there was a node here, a node there, and another, which is one. So between these two nodes, there's this branch. So how many branches? There's also another node there and another node there, and there's one branch. There's also one node there, node. So there's also one node. So here we have, how many branches do we have? We've got about 1, 2, 4, 5. We've got 5 branches. Now we want to find also how many loops. Now we did mention what a loop is. If you come back to the definition, it says a loop is a collection of branches that form a closed path returning to the same node without going through any other nodes or branches twice. Now if we see here in terms of the loop, if we start from point A, it's not difficult to see that we could have 3 loops. Actually, there are more than 3 loops if you consider the internal loops. But if I start from A, for example, right, I could have this one loop going like this, returning to A as 1, right? And if I have to look at A again, I can also have this inside loop here that goes like this, and again I can return to I, right? And I can also have another loop within this point, but that is not mentioned because if I look at B as well, there's this also another loop there. If I look at C, there's also another loop there. But if I look at the point of reference to be A, then definitely with reference to node A, in order to retain making a closed path, then definitely if I look at A, I'll have actually about 3 loops. Now, very important to understand this point, guys, because then when it comes to solving some of these loops are going to be used very often. Now, if we look at the Kirchhoffs voltage law, which is the KVL, what does it say? What does it say? So it says the algebraic sum of voltages around each loop is 0. So if I take any loop and I add up whatever voltage drops and whatever sources of voltages that are in the loop, they will have to add up to 0. Now you need to understand that when we talk about KVL, we also have to adopt certain rules, which at some point, based on your understanding, you could adopt these rules, but they are not standard rules. Now I want to mention this because sometimes things may change. One textbook may treat this rule as the other. Now for the purpose of this video, we're gonna adopt such a rule. Beginning with one node, add voltages across each branch in the loop if you encounter a plus sign. So if I have a plus sign that I encounter on the voltage drop, then that voltage will be treated as a positive. So beginning with one node, add voltage across each branch in the loop if you encounter a positive sign, and subtract voltages if you encounter a minus sign. Just simple as all that, and I'm going to show you in the next slides what that means. So if we look at the summation, what are we saying? We're saying that the summation of the voltage drops minus the voltage rises is equal to what? Is equal to 0. Now what it means is that if we have the positive voltages and the negative voltage, so in other words, what we're saying here, we could have the positive voltages, those that start with a plus, and then we could actually also subtract those that actually start with the minus, and we should get equal to 0. Or we can say that the voltage drops are equal to the voltage rises, and we're gonna see this with an example. So now Kirchhoff's voltage law around the first loop. So for example, if we have a loop like this one, right? Now we want to make an algebraic equation of the voltages. How can we do that? So first of all, we take this loop around, and we want to say that the algebraic sum of every voltage drop plus the voltage rise is equal to 0. So the first thing I want to teach you guys is the concept of the passive element analysis. Now I want you to understand that in here, for example, with the current, when the current flows into a passive element such as a resistor, it's going to leave a plus here, and where to go out through is going to leave a minus. And for sure, if current comes through all the way, when it reaches, this is a point where when current reaches, some current will definitely have to go that way. Some current may go this way, and some current may go that way, and some current may go so that way. At this point, we can have I2. We can mention that there's I2 that goes through R2. You can't say that this is the same current that goes through around node, because here is a junction. And when there is a node, so whenever current reaches a node, the current must branch. And so we look at this loop, and then what we say about it. We say we need to assign current variables and directions. That's the first thing we need to deal with. Now, assigning current variables and directions, this is what we experience. So we're going to see here that use Ohm's law to assign voltages and polarity consider with passive devices. Current enters at the positive side. That's just like I said. Now let me just show you what this means. So you can see here that as soon as this enters, right, we can have a plus there and a minus there. All right. And if you check here again, that if now we'll try to look at what happens here, we can see here again, as soon as I2 enters into this resistor, it leaves a plus there and a minus there. Now what we say about it. So starting at node A, we can start at node A, and at the first voltage drop, we can see here that because this current enters, if as we are driving around the loop, first of all, what are we saying as we're driving around the loop? If we start from node A, we can see here that we start with we enter a positive terminal. So therefore, the first voltage drop will have a plus here and another one, right? And now when we travel again, we reach here again, we enter with a plus, the second voltage drop. So we have to add I2 plus IR1, I2 plus IR2. Right, this is what we have. So we have I2 plus I1 plus IR1 plus I2 plus IR1. Now here, notice that as we travel, so we started traveling from here, as we come through this way, as we try to enter, we first meet a minus. So therefore it's going to be minus Vs. And that, since we've traveled around the loop and we've reached A, that could be equated to 0. Notice the sign of each term matches the polarity encounters first. Now, when given a circuit with sources and resistors having fixed values, you can use Kirchhoffs two laws and Ohm's laws to determine all branch voltages and current. So if we have a question like this one here, where we have to find the voltage across the 7 ohm resistor, well, if we have to use Kirchhoffs voltage law and Kirchhoffs laws in general, here this question for sure, if we have to find the voltage drop, can be approached in two ways. The first way is to use Ohm's law, where we add the summation of this and then divide into 12, finding the current that is flowing. So the voltage across this is simply this current times 7 ohms. But then if this is the same current that is traveling around this series circuit, then we can come up with an equation which again looks at the summation of voltages within the loop is equal to 0. So if we have to put our polarity, if this is the current that is flowing, then this is plus minus. It's also plus minus. Then we can travel around this loop. So if we travel around the loop, then definitely we shall have positive VAB plus VBC, and then we're going to have minus 12 volts is equal to 0. So if VAB is I times, so VAB is this current times 7 ohms, and VBC is equal to I times 3 ohms. Now by KVL, we know that VAB plus VBC, because we know that now we can travel around this loop. If we travel around the loop, we start with a positive, so this is VAB. And when we reach here, where this is plus VBC and this is minus 12, is equal to 0. Now we can substitute the respective values. We've got I7 ohm plus I3 ohm minus 12 is equal to 0. Now for here, we can solve for I and we can find that the current is 1.2 amps. Now since VAB is I and VBC is there, we can just multiply 1.2 amps times 7 and VBC times 1.3 amps. And now we can have an I is equal to that. So VAB is that and VBC is that. So KVL, we have this I times 10 over my total. So I is equal to what? That. From the viewpoint of the source, the 7 and 3 ohm resistance in series and equivalent to the 10 ohm resistor. Now to the rest of the circuit, series resistors can be replaced by an equivalent circuit resistance equal to the sum of all resistors. So if you have resistors that are in series, you could actually add them to form one resistor, which is simply a summation of all those resistors in series. Now, what does the Kirchhoff's current law state? The algebraic sum of all currents entering a node is 0. Add each branch current entering the node and subtract each branch current leaving the node. Okay. Now we can say that currents in minus currents out is equal to 0, or currents in is equal to currents out. Now Kirchhoff's current law. Now here, if we have to assign current variables and direction, now since we say that this is just like treated like one node, this is treated like one node because we have a node there, though we have a node there, and there's no potential drop between elements. So there are no elements, so this one is treated as one node. But notice that with respect to B, we have some current that I2, with currents like I2 going out of the node, and I3 going out of the node, and I1 going into the node. So if we have to obey the Kirchhoff's current law, where we add those which are coming in and subtract those, then this is going to be I minus I2 minus I3. And then of course this one is also going into the node, so it means all those that are entering, we add them. So it's I minus I2 minus I3 plus IS is equal to 0. Let's look at some circuit analysis that we have here as a question to reckon with and see how you can solve it. So you can use Kirchhoff's voltage law and Kirchhoff's current law to solve such a question. Now this question just demands that you calculate the values of A and B. Then I use the Kirchhoff's voltage law and the Kirchhoff's current law to find a solution. Now by KVL, what we can do, we all know that if we can, to solve this question, what we can do, if we can calculate the value of I2, then we can multiply I2 times 4 amps. Now once we know I2 times 4 amps, then we can count within the potential, this potential drop for the circuit parallel rules. When we get this potential drop is the same as VAB. So what we can do, therefore, we can look at the loop of interest in trying to solve for KVL. So we can look at this loop which involves I2, because if we get I2, we multiply by 4, then that becomes VAB. So therefore, in looking at this, we can have this as our equation of interest. So what can we do? We can travel around the loop in this manner to find the algebraic sum of all the voltages. So what we do, so therefore if I look at this and I travel like that, and if I have to start with I1, then I can say that minus I1, because I'm entering from the negative, times 8 ohms plus, because I'm entering 9 to the positive, plus I2 times 4 ohms is equal to 0. This is a good equation. Now from here we can solve what I2 is. I2 is equal to 2 times I1. Now 10 amps is equal to 1 is equal to, so we can say that this 10 amps, because now we know for sure that according to Kirchhoff's laws, if this node, two nodes are like one, then definitely, if this is also a current source, then definitely 10 amps minus I1 minus I2 is equal to 0. But we know that 10 amps is equal, in this case we can make 10 amps subject, and we have I1 plus I2, and we can replace this I2 in there. And once we do that, we can have such an equation in which I1 can be found to be, so I1 is equal to 3.3 amps and I2 is equal to 6.67 amps, and VAB is 26.63 volt. Now this is a circuit simulation that really gives you the results that you're looking for, because if you see here, really this is 3.3 amps as calculated, and this is 6.67 amps as calculated, and this is the voltage that we were looking for, and that's the result that we get. Even by software simulation, this is being verified. All right, and so there we have it, and we can also do it by Ohm's law. Now Ohm's law, you treat this one as a closed circuit, but we can also, by Ohm's law, if we know by Ohm's law, VAB is equal to, now by Ohm's law, what we can do here, we can find we can find this resistor here. Now these two resistors are in parallel, so we can find the equivalent resistance, and that equivalent resistance will be the one that we have in parallel with this. Now if that is in parallel with this, and this is an open circuit, it means the equivalent resistor times the current in amps will give us what VAB is. Now real quickly, let me show you. For example, this is the equivalent resistance. How did we get it? Well, if you multiply 8 times 4 divided by 8 plus 4, you get 2.667. And if you multiply 2.67 times 10 times, you can then get that, and that is VAB. Okay, so this is how we add circuits in parallel, and you've seen all of this. Parallel resistors, that's the formula. Now solve for the current through each resistor and the voltage across each resistor. So this is what the question says. Now if you see here, the circuit is a bit more complex as compared to the one that we did, but also I want you to understand that if we can take I1 as the current that is coming in, and I2 as the current that is going this side, and I3 as the current also that is going that side, it's still right. I'm going to teach you some method as we go on. Solve for the current. So we need to solve for the currents that go through each one of these resistances. How do we do that? Now I want to show you that by way of simulation, these are the results that we get. Right, and therefore by calculations we should pretty much get the same results. Now using Ohm's law, add polarities and expression for each resistor. So if this is current I1, so this is what we begin to see. Okay, we begin to see a potential drop across. That one is positive because this current is going to be positive if we're going to travel like this. And this one as well, we see I3 to be also a positive, and we see I4 current across the forms is going to be that, and this one is also going to do that. So we're going to look at all those parameters. So we can take the first loop here. If we take the first loop right here, then we can travel around. How do we travel around? Well, it's not difficult to see that if you start from this side, I1, then this one is going to be positive. This one is going to be positive. And this one, traveling like this one will be minus. And that's the equation that you get. If I look at the loop 2 here, right here that we have, the loop 2, it's also not difficult to see that you can say that this, you can start. So if we start from -2, if we start from here, if we start traveling around this like this in the loop, then definitely this is -8 minus 2 times 8 ohms plus I3 plus times 6 ohms, and then plus as well I3 times 4 ohms. And if we solve, or I2 is equal to this, and that's what we get for I2. Now write Kirchhoff's current law equation at point A. If we write the Kirchhoff's current at point A, because this is a common point for all of these three, now it's not difficult to see that this one here for Kirchhoff's current law, we can take that those that are going through the node, they're treated as positive, and those that are going out are treated as negative, and this is what we have. We now have three equations in the three unknowns, so we can solve for the current through each resistor that are used to find the voltage across each resistor. Since this one is equal to that and that one is equal to that, then substituting into the first KVL equation, we can substitute I2 plus I3, which gives us I1. And so what we can do here, we can solve the equation in that manner. And what we have is that we have from the second KVL equation, I2 is equal to that. substituting into first equation that value of this, or where I2 is, we substitute with that, and this is what we have. And so you can see I3 is equal to that plus that plus that, and I3 is equal to this, and now we can see that I3 is equal to 50 plus, and I3 is equal to 1.538. Now if you check in my simulation right here, I3, if you go through it, you see that this is our I3, which is equivalent to 1.538. Okay. Now we can also check out in this. So I3 is equal to that, and there was a relationship between I2 and I3, and this is exactly what you get in terms of the response. And now we can also since we know I3 and I2, then we can use Kirchhoff's current law to solve for I1, because I1 is simply the addition of these two, and that's 3.461. And for sure I1, if you count to this, you could actually see for yourself that this is 3.42, which is what we found. Now if I go back again, then it's not difficult to see that I can now check and calculate every voltage across. So this is the case. Now I1 times this, that gives me 34.6 volts, and I2 gives 15.3, and this also gives me that. Now, so for the currents that each resistor and the voltage is substituted in series and power simplifications, you can use the series and power simplifications by simply looking at these two and then make it as one. If you make that one as one, then you have a number 10, then you can actually use, if you use this method, you can actually use the cage, you can actually use the principle of combining this into one resistor. If you do that, you've got 4.4 ohms, and these two resistors will be in series. And if they are, then you can actually add to that 14.4 ohms. So if you want to write a simple KVL based on this, if you have to, well, you could use it actually. So you can say 1.1114 minus this is equal to that. And if you do that, you can calculate what I1 is, just like we found it. Then I1 times that becomes the voltage drop. So the voltage drop across the 8 ohm resistor is 15.4. If I2-8 is equal to 15.4, then I2 is given as actually that. And so by KCL, so we can verify and find all the results. Now guys, I'd like to end right here, and I want to advise you to go through this question. And next time I'm going to look at a more complex circuit in trying to help you understand the principle of KVL and KCL. I'd like to thank you for viewing, and see you in the next class, where we'll be able to tackle this question and solve for the current that flows in each resistor. Thank you so much for watching.